Let us next see this example. Here we see a function f from the set consisting of the numbers 1, 2 and 3 into the set consisting of the letters a, b and c. And the function is this: f of 1 is a, f of 2 is b and f of 3 is c. It's a bijection or a bijective function, which means that it's both 1 to 1 as well as onto, which you can clearly see. The function is 1 to 1 because distinct inputs have distinct outputs, and it is onto because every element in this second set, the codomain, is the f image of some element in the domain. Now we have to show that there exists the function g from the codomain of f into the domain of f, such that g composition f is the identity function on this set, and f composition g is the identity function on this set. So this is how we define the function g. G of a is 1, g of b is 2 and g of c is 3. So essentially this is just inverting the arrows in the arrow diagram for f. F maps 1 onto a, so g maps a onto 1, like that. So then with this g, let us calculate g composition f. If you go back to the definition of composition of functions, you will see that the domain of g composition f is the same as the domain of f, and the range of g composition f, or rather I should say codomain, in this case it will be range, but in general codomain of g composition f is the codomain of g. So what is the domain of f? The set 1 to 3. And what is the codomain of g? The set 1 to 3. That means this composition is a function from this set into itself. And let us now calculate it at the input 1. By definition, this is equal to g of f of 1. Now if you remember, f of 1 is a, so this becomes g of a, but g of a is 1. So that way this composition does not change 1. Your input is 1, output is also 1. Similarly, if you calculate the composition at 2, you get g of f of 2. But f of 2 is b, so you get g of b, but g of b is 2. So you get your input back. And that is also the case with g composition f of 3, which is g of f of 3. f of 3 is c and g of c is 3. So that is why this function does not change any of the inputs. But that is precisely what the identity function on this set does. That is why this is nothing but the identity function on the set 1 to 3. Next we calculate f composition g. The domain of f composition g is the same as the domain of g, which is the set of the letters a, b and c. So let's calculate it at a. This is f of g of a. G of a is 1 and f of 1 is a. So again here also you are getting the input back. Similarly, f composition g of b is f of g of b. G of b is 2 and f of 2 is b. You get your b back. And just like that, this one also gives you c back. That means not only is this a function from this set into itself, but actually it does not change any input. It gives the input back as output. That is why it is nothing but the identity function on this set. So based on that example, we have this next definition. Say you have a function f from x into y, and it is said to be invertible if there exists a function g from y into x, like the previous example, for which g composition f is the identity function on x and f composition g is the identity function on y. And in this case, the function g is called the inverse of f and is denoted by this notation f inverse. So the g that we defined in the previous example, that is the inverse of f, and because g exists, that f is invertible. But this definition raises a question, and the question is the use of the definite article the here. The definition nowhere says that g has to be unique It simply says that if there exists such a function g for which these two things happen, then f is said to be invertible. What is the guarantee that whenever a g exists, that is the only g? Maybe more than one g exists. So in that case, is it okay to use the? Actually, whenever g exists, it will be unique. That is why the use of this definite article the here is justified. That, however, needs to be proved. I won't do it. It's also not given in the book, but I want you to think of it. It's not very difficult to prove that whenever there is an inverse, there is only one inverse. Now let us see another example next. You first consider the set y consisting of all numbers like this 4n plus 3, where n is any natural number. For example, if you take n equal to 1, then you get 7 here. So 7 is an element in this set, like that. And then you consider this function f from the set of natural numbers into y, given by that formula, f of n equal to 4n plus 3. We have to show that this function f is invertible and we have to find its inverse. Showing that f is invertible means finding a function g like this, which maps y into n because f maps n into y, for which those conditions in the definition of invertibility of a function are satisfied. And our guess is that this g will work. G takes an input x from y, which is some number like this, and the output is x minus 3 divided by 4. I will tell you about how I came up with this formula. Now, what is it that we have to do? First of all, we have to see that g is in fact a legitimate function. Is it not a function? It looks like a function because for a given input x, obviously this is going to be some number, but that some number has to be a natural number. That we have to be sure of first, and then only we can go for showing that those conditions, that g composition f should be the identity function on this and the other one, are true. So that's what we do next. We take any element x in the domain of g and we want to make sure that the output lies in n. Now, what does it mean for something to be in y? It means that something looks like this by the definition of the set y. It will be equal to 4n plus 3 for some positive integer or for some natural number n. Now, with this information, let us see what the output becomes. So, g of x by definition is x minus 3 divided by 4, but x is 4n plus 3, and after the necessary cancellations you find that it is n, which obviously is a positive integer. So yes, the output actually lies in n, and that is why this function makes sense. And we express that by writing hence g is well defined. And next we go for showing that those two equations are true in the definition of invertibility for this g. One of the equations is pretty easy to show, namely this one. G composition f is the identity function on the set of natural numbers. For that, what we do, we choose any natural number n and apply g composition f on that n. By the definition of composition, that is equal to g of f of n. And if you go back and see the definition of f of n is 4n plus 3. And how did I just simply write that this is equal to n? Because luckily we have the calculation here already done for us. Because if x is 4n plus 3, this g of x is g of 4n plus 3, and we already know that that is equal to n. So your input is n, output is also n. G composition f does not change any element of the set n, so it's the identity map on n. Next we show that f composition g is the identity function on y. So accordingly we take any element y in y and just straight away we apply f composition g on y. So by definition of composition, that is f of g of y, and g of y by definition is y minus 3 divided by 4. And f of that, what does f do? F takes the input multiplies the input by 4 and then adds 3 to it. So 4 times this plus 3, and you can clearly see that in 2 steps. In the first step you are going to cancel these 2 4's, that will leave you with y minus 3 and plus 3. So in the second step, after cancelling minus 3 and plus 3, you are left with y. So here also you get back your input. That means f composition G does not change any element of y. So it's the identity function on y. So this is what we need in order to claim that f is invertible and G is its inverse. So you can write your final conclusion like this. So f is invertible and the inverse of f is G. So next we address the question of how to find a formula for G. Your f is given to be this function, f maps n into y, and f of small n is 4n plus 3. G is supposed to map y into n, but what is g of x? To find g of x, you can use this relation. F composition G of x should be equal to x, and this x of course is coming from y, and this f composition G, if such a G exists, should be the identity map on y, and that is why this thing should happen. So that means what? F of G of x should be equal to x, but you know what f is, so this becomes 4 times G of x plus 3. That should be equal to x, from which if you solve for G of x, this is what you get, and that's how I figured out what G should be. Next example is also similar. Here the set y is the set of squares of all the positive integers. So that means you will have these positive integers in this set 1, 4, 9, 16 like that, and we have defined the function f from n into y, which is the ordinary square function with natural number inputs. So here of course it's very easy to see how f is a function from n into y, because precisely these are the outputs and those outputs form the set y, and then we have to show that this f is invertible and we have to find its inverse. Guessing the function g in this case is easier than in the previous example, because f is the square function, so we take g to be the square root. Here also, however, you have to show that this g is well defined. So let us first write the things that we need to show that g is well defined, and then only we can go for showing those two equations. So we start our work by taking any element x in the domain of G, that is y. Now by the definition of the set y, x will look like this, the square of some positive integer n. Now what will happen if x is simultaneously the square of some other positive integer? And by other I don't necessarily mean something different from n. We are just simply saying that if x is simultaneously n square and m square, where m is also in n in the set of natural numbers, then what happens? Then m square becomes equal to n square, or this or this. Now note that m and n are both natural numbers, that means they are both positive. So their sum is also positive, that means sum is not 0 in particular. But when the product of two real numbers is 0, at least one of them has to be 0. So that means the other one has to be 0. So from that you get that m has to be equal to n. That means this n is unique. There can only be one such n whose square is that given x. And now with this information we calculate g of x. X is n squared, so g of n squared is square root of n squared, which is equal to n. But this may remind you of my only short video. Is it okay to write n here? You think about it. Actually there is no problem, but there would be a problem. There would have been a problem if n were a negative number. But why? I won't say why, but here there is no problem. So what are we getting? For that chosen x, g of x is n. which is a unique element of n. Not only is this n itself a natural number, but n is unique. So for a given input, you are getting a unique output, only one output. That is why g is a function, or in other words, g is a well-defined function. And now we can work with g and see if the other two equations are true. So one of those two equations, namely this one, g composition f is the identity function on the set of natural numbers, is pretty easy to show. So you take any n in n and apply g composition f on that. So that is equal to g of f of n. F of n is n square, and you already have the calculation here. This is equal to n. So you get your input back as your output, and that is why g composition f does not change any natural number. So it's the identity function on the set of natural numbers. For the second equation, that is this one, we take any element y in y, and we straight away apply f composition g on y. That is equal to f of g of y, and g of y is square root of y, and f of square root f does what? F squares the input. So you have square here, but already there is a square root. So cancelling square and square root, you have y. Again, be very careful. Let us take a moment to think of square root of y. Is it okay to take square root of just about any number? Well, if you want to be inside the system of real numbers, then you have to be careful when taking square root. You should not take the square root of any negative number. But what about our y? Is y negative? No, y is not negative. Y cannot be negative. Why? That is because you go back to the definition of the set y. Y is what? Y is the set of squares of all positive integers. So not only is y not negative, y is also not 0. Y is positive, and y is in fact a square number. So it's okay to take its square root, and after cancelling square and square root, you are going to have y. So here also again, any element of y remains unchanged under the application of f composition g. So f composition g does not change any element of y. So that's why it's the identity function on y. But then we have both the equations, and we can now declare that f is invertible and its inverse is this square root function g. Next we have this example where a function f is given from the set of natural numbers into the set of real numbers. And this is the function. F of n is 4n square plus 12n plus 15, a polynomial, quadratic polynomial in n. Now it's not the function f that we have to show is invertible, but something else derived from f. Let capital S be the range of the function f. That means the set of all output values of f. Or in other words, all numbers that look like this, where n is some natural number. And next we define the function g from n into s. And the formula of defining g is the same as the formula defining f. That means g of n is also 4n square plus 12n plus 15. But the difference between g and f is that the codomain of g is s, not r. And we have to show that this g is invertible, and we have to find its inverse. So we start the solution by looking at any element in S, because our aim is to find a function for the given function g, such that the codomain of that function is n and the domain is S. So we start by taking any element y in S. Then by the definition of S, because S is the range of f, so any element in S will look like this. So y is equal to 4n square plus 12n plus 15 for some natural number n. But now let us manipulate this polynomial, this quadratic polynomial. In place of 4n square, you can write 2n whole square, and 12n you can write like this, 2 times 2n times 3. And in place of 15 you can write 3 square plus 6. So we are completing the square. This portion becomes 2n plus 3 whole square. So because it's a perfect square, it can never be negative, it's greater than or equal to 0. So you have plus 6, so this entire thing will be greater than or equal to 6. So you learn the fact that any element in S is greater than or equal to 6. And now we will define that other function which will map S into N and show that G is invertible. So this is how we define H. H obviously will be defined from S into N, and the formula is this. H of pi is square root of pi minus 6 minus 3 divided by 2. Again the question arises, how did we figure out H? Well, that comes from here, that y is equal to this, from that itself it comes. Actually, how does it come? From the fact that y is equal to this, you solve for n, you express n from this equation in terms of y. N becomes equal to this. We will see that right now. But the point now is this. Is it first of all okay to write square root of y minus 6? You see that there are two places where you may have problem. You are taking square root and you are dividing by something. Division is not a problem because the number you are dividing by is 2. 2 is not equal to 0, so that causes no problem. But you may have a problem here if y minus 6 becomes negative, because then you are not getting a real number. You will get a non-real complex number. But luckily, y is greater than or equal to 6. So y minus 6 is greater than or equal to 0. It's not negative, it's non-negative. So that's not a problem. So at least this expression gives you a real number. But we don't just need a real number. We need our output to be a positive integer. So we need to show that right now. So you take any element y in S, and then we already know that y is going to look like this for some positive integer n. So we use that information here and then calculate h of y. So h of y by definition will be this. In place of y, you will have the square of 2n plus 3 plus 6. And then you can just see that everything just cancels out in a very nice way. I have not shown the full calculation because you can do it yourself. First, 6 and minus 6 will vanish. Then square root and square will vanish. You will be left with 2n plus 3. Then 3 minus 3, they will vanish. And finally, after cancelling 2, you are going to get n. So n is of course a positive integer, so it belongs to this. And I have just simply hastily written that so is h is well defined. But is it enough to say that h is well defined? Actually, there is one more thing. We have shown that for any y in S, the output is inside n. Okay, but what is the guarantee that that is the only output? Are we not going to get something else? And that question can be answered by choosing another expression like this, where in place of n you have possibly some other m, say like that one, the previous example. But if that's the case, then n should be equal to m. Why? Because if 2n plus 3 whole square plus 6 is equal to 2m plus 3 whole square plus 6, then after again a sequence of cancellations, you will be able to say that n is equal to m. That is why I did not bother to write that part, but actually you should write that part. So now only we have shown fully that this h is a function, a legitimate well-defined function. And for this h, now we can go for showing that those two equations are true. That will enable us to say that that function g is invertible and h will be its inverse. So first we show that H composition G is the identity function on N, and for that we take any element ending N and apply H composition G on that element. So that is H of G of N, and G of N by definition is 4n square plus 12n plus 15. But that is equal to, you already know, the square of 2n plus 3 plus 6. And I did not erase this part because this is just this calculation. H of this, you think of this in place of y. H of this is just this, which is equal to n. We already have that done for us. Why do it again? So that is equal to n. So you are getting your input back as your output. That means H composition G does not change any natural numbers. So it's the identity function on the set of natural numbers. And for the other equation, we take any element y in S, because now we have to show this. G composition H should be the identity map on S. And again, same thing. Y originally looks like this, 4n square plus 12n plus 15 for some positive integer n. But you already know that that is equal to this. So straight away we have written just that. Y is equal to this for some positive integer n. And now we apply G composition H on y. So that becomes G of H of y. But we have already done this calculation twice. H of y is equal to n. That one, having square root, all that thing. But now you are having G of n, and G by definition is this, which is this. But this is just your y. So that way here also you get your input back as your output. So this function does not change any element of S, so it's the identity function on S. So we write the final conclusion that G is invertible and G inverse is H. After these examples, there is a result in the book which says that function composition is an associative operation. Ideally, this result should have been present immediately after the definition of function composition, but it has been misplaced. Now, after dealing with invertible functions, suddenly it is appearing. So this is the problem with this book. This is not the only problem, there are other problems also, and I think all these problems are generally present in any NCERT book. Lack of organization and the problem of presenting the things in a manner which is unnecessarily confusing. In fact, the definition of invertible functions that you saw today, that is there in the book, that a function is invertible if another function g exists for which so and so things happen. It's not the most natural definition. Naturally, invertible functions should be defined by linking them directly to one-to-one onto functions. That's the most natural way of doing things. But of course, NCERT book is NCERT book. I try to present the things as accurately as possible, but I cannot do anything about this organization. So things like this will happen. Things will just spring out of nowhere suddenly without any rhyme or reason. So I will just simply pick things up from the book and present them as they are. I mean in the sequence that they have appeared in the book. You may have noticed one more thing. In the book they have defined the inverse of a function, but did not bother to say why it is unique. But they kept on using the inverse, the inverse. We can ask a natural question, right? Why should there be only one inverse when it exists? There is no answer in the book. But we have to do what we can do with this book. I hope it gets over quickly. So that will be all for today. So see you in the next video with more things. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.